Welcome everybody, and it is my great pleasure to be speaking to you today. And I will today try to give you a overview of what some of the research is about at chemical engineering, because I thought if I share with you some of the research, then you're able to relate that to what maybe some of you would be interested in chemical engineering and studying chemical engineering in the future. But also importantly, as the title of my talk says, circular economy equals CE, the acronym, equals chemical engineering. So I would like you to also take home some messages around circular economy, sustainability, and emissions, carbon emissions, and net zero, and how we in chemical engineering are tackling some of those grand challenge problems. So as you are fully aware, waste is a big problem. It's a big challenge, not just for Australia, but globally. As you can see on this slide here, which my research group has put together, collecting data from different countries in terms of their development versus in correlation with the waste generation. On the y-axis, you can see the waste generation. And for example, the GDP, which reflects the development of a particular country, is increasing the waste generation increases with the increase in GDP, which tells you that countries, as they develop, are producing more waste. So it is a global problem, and we all, as individuals, have something to contribute in waste. We need to attack and address that challenge. So what does that mean in terms of what the topic here, the circular economy? Currently, we have a linear economy, which is the way we operate as business as usual. And the linear economy is what is exemplified on the slide here. We extract resources from nature, and then we produce products, we distribute them, we consume them, we are the consumers, and we then dispose of them at the end of their life into the landfill, for example. And we in Australia, we use landfill technology, landfills, as a significant way to deal with our waste. But importantly, in this slide, you could see that CO2 emissions, carbon emissions, and water and emissions to water and land is also quite important. At every step of the life cycle of any product, we have emissions productions. That's the linear economy. What about the circular economy? The circular economy, you might have heard about it, is an important paradigm shift from the linear economy. It's a systemic shift. It means we have to change many things in our society, in our supply and demand, in our consumption patterns, in our production patterns, and so on. But essentially, it is very much pivoted around the first step, which is the design step. It is the very foremost step in the circular economy. And design of products here is very important. How we design them ultimately dictates how much waste we end up generating. So think of any product around you in the room, in your house, in your community. Any product is designed in a particular way that ends up good or bad for in terms of waste generation. So we know that is very important. We've got to design products that are lasting longer and they can be reused, not necessarily recycled, rather reused. And that's important, as I will explain in a few examples of our research. So we know also that emissions is very closely linked to this shift to the circular economy, with about 40% of emissions can be mitigated simply by shifting to the circular economy. So what is the circular economy? Think about it for a few moments. Hopefully by the end of the presentation, you will be able to understand a little bit more about what that is and how also it is embedded inside chemical engineering discipline. Let's take the example of solar panels. You know, solar panels produce electricity from solar energy, and that means we can have a renewable energy source on our rooftop. In Australia, it's one of the leading countries in the world in developing the solar rooftop installations. It's got about 54 million solar panels installed on the rooftops so far. That's my estimate, approximately. And that's about 30% of the current homes. That's only 30%. That means, in my rough estimates, that this is about, if you line them up end to end, it's about 95,000 kilometers of solar panels. Think about that distance. It's about 2.4 times the length of the equator. It's also, if you stack them up just flat on top of each other, it's about 214 Mount Everests. It's a large quantum, and the numbers go on and on. It's a large volume of materials. So of course, when we say solar panels, we are referring to energy. But when we also, in chemical engineering, we deal with materials. Materials balances, energy balances are very important, and they work together very much. And here, in this example, we do a calculation called life cycle analysis. Basically, it tracks all the materials that go into the making and the manufacture of solar panels, and then we assess that from an environmental perspective. You've got glass, copper, aluminium, tin, lead, and many other things go into the making of such a product called the solar panel. So when we assess that kind of from a sustainability perspective, then we start to learn that in this figure here, you could see this assessment across all the life cycle, resources, extraction, manufacturing, logistics, transport, consumption, etc. The bar here compares landfilling the solar panels versus the two different types of technologies to recycle solar panels. That's the top right bar chart in the slide. And the y-axis for that bar chart is kilograms of CO2 equivalent per kilowatt hour. So to produce 1 kilowatt hour, we need 0.06 kilograms of CO2 equivalent, or we will produce that much CO2 if we landfill them. But if we recycle them, the other two bars, you could see recycling solar panels, that's what the results here says, is only slightly better than landfilling them. So that's quite a controversial finding, right? Because we are saying solar panels are very good, and they are good because they do give us solar energy for the use and consumption in the home and in the commercial and industry. But also it is important for us to make a new conclusion. And this conclusion is back to my first point about design. We do need to think about how we design these solar panels for the future. They need to be sustainable much more in terms of their material consumption. And that means we need to source the right materials. We need to design them in the right way so they are very, very efficient. And this message continues on and on in terms of all the other technologies, not solar panels alone, wind energy, any other renewable energy. And think about this 2020 figure. We've only got 10% penetration of wind and solar in the world electricity generation. In Australia, we still use coal power quite significantly, and renewables is only about 27% in 2020. It is going up, that's very good. However, what I'm saying that it is very important for us to understand the impact of these technologies, these renewable sources on the environment. It basically means there is an environmental cost for any technology that we bring in. And in chemical engineering, we focus on that problem quite significantly. How we don't only think about energy, we think about it together with materials in one silo. It's not single treatment. It is important for us to understand the interplay between energy and materials. And that's a big focus for us in chemical engineering. So how do we do things? How do we design these systems for the future? How do we, and this is just one example, solar energy. We have many examples in fuels, pharmaceuticals, food, and agrochemicals, etc., etc. Chemicals manufacturing, all of that needs design of these manufacturing facilities, these chemical plants, and we've got to do that in a very sustainable, circular way. So, and we need a strategy, and this strategy we can adopt is in my research, we focus on process systems engineering. It's systems thinking. So we bring all the systems across the different scales, from the atomic scale all the way to particles, systems, plants, cities, and so on. Even the climate, we do that. And we approach this by modeling. So we use a lot of algorithms. We write code. We develop programs for modeling these systems, and we connect these systems together in the models to be able to achieve higher efficiencies. And also we connect that to the markets and the policy. And we also don't forget about circular economy always. That's a really important objective for us in our research. This research, process systems engineering, is very strong internationally. It's part of chemical engineering, and it has a very strong international research community. It was developed by Professor Sargent from the UK a few decades ago, and it is contributing quite a lot in the industry in different sectors. And we develop our research so it is very practical. It applies to society's problems, like I said, waste, energy, and food, water, and chemicals, and so on. And we try to develop processes that move up the technology readiness scale, TRL, to be able to commercialize these technologies. And very often in our school, we commercialize. We take our research out into the industry. We make opportunities by creating startups, companies, spin-offs, and we make business out of the innovations that we have been working on. This is a slide that shows you this multi-level way of thinking about this problem, where we can have the plant at the bottom, supervisory layers, optimization decision-making layers, and then the policy. This is the multi-scale system I was referring to, and we often publish on this work in the international journals. Our research uses that systems thinking approach. It uses that process systems engineering, digital approach, modeling, optimization algorithms, and it couples it with circular economy and net zero domains to solve those grand problems in waste, circular economy, materials, and net zero emissions. We focus a lot on that. And we use this approach across those scales. I have many examples here I can show you, and I'll share one or two just in the interest of time with you today. And of course, at any time, you're always welcome to reach out and talk to us and talk to me if you wish on these different examples and future research that we are working on at the different scales. So I'm going to start with the first example, which is circular design and system strategies for molecular scale. And this is how we can capture carbon dioxide in large emitting plants or even small ones. And we can compute at the molecular level the design of the molecule that is the best molecule for capturing the CO2. It's just like that carbon dioxide in the soft drink that we all drink, and that's absorbed inside the drink. This is very much at very, very large scale. How do we develop a process that can achieve this carbon capture and reduce the emissions from plants such as power plants that emit the CO2? We design the carbon capture plant, and what we do, we are kind of architects. You know, the architects, they design buildings and structures. We design chemical plants. We design products in our discipline. And this is such a process or a plant called carbon capture plant, very important. You will hear much more about this type of plant in the coming months and years, because it is going to be an important process in capturing the CO2 for us to achieve the net zero targets for the future. So here the CO2 is emitted from the plants on the left. It's absorbed in an absorber column. It's a very big tower. And this big tower then is taking the CO2 into a separation unit downstream, and then it purifies it. You can see the purity of the CO2 on the right is at about 98%, with about 90% capturing rate. So 90% of the CO2 that comes in is captured by this plant. So it's not emitted into the atmosphere. That's the advantage of this, and that's the purpose of this. However, remember what I said earlier, there is an environmental cost. There is an energy cost. Where is the energy going to come from that is going to run this plant? We need energy for compression, for heating, for pumping, and so on. And this solvent that is, like I said, like the example in the soft drink that I gave, that solvent makeup is very important. And this whole process can consume about 20% of the energy of the of the power plant, for instance. So you could see this kind of trade-off, this balance, this efficiency sweet spot that we need to find always in these problems. And this kind of process is very becoming very, very important, as I said earlier, and it will be also applicable in the direct air capture. You might have heard about this. Elon Musk himself has developed a $100 million prize for solving this problem, which is using direct air capture technology, capturing CO2 and pulling it out of the atmosphere. And that's, of course, very important for sustainability purposes, because internationally it is almost very much agreed by most scientists that it is now important for us to remove carbon dioxide from the atmosphere to be able to meet our 2050 targets and reduce and make sure we are below the 1.5 degree global warming limit. So that's another new technology that's emerging, direct air capture, and chemical engineering is very important for that, and designing these plants and the materials that absorb that CO2 is very important. How do we do this? We do it through intelligent algorithms, AI, if you like, artificial intelligence or machine learning code algorithms, and we compute the material that best does this. We do this calculation in the computer, and we find the best material that does the best efficiency to capture that CO2. This is big business also. Don't forget, there is billions of dollars involved in this. This is not for just fun. This is definitely something that is also economically profitable for some companies. So being sustainable is important. Being profitable, economical feasibility is very, very important. And here what I want to highlight is the fact that I come back to my first example where I said we go to the molecular level, and then we also go to systems scale, big scale. And this is a good example of that. So here what we do is we have models of how these molecules interact with the CO2 inside the process. And we put that in the computational code. We optimize to maximize, for example, the efficiency, or to reduce the energy of the capturing plant. So then that means we can achieve the best molecule that can do that. And we've done that. The results in the table on the right show that how much we can reduce this energy duty for capturing each kilogram of CO2 by computing a new solvent for capturing that CO2. So that's a good example, and we've used such a method of computational artificial intelligence algorithm to compute many different materials for many different processes. Some of them are listed here on this slide, including heat pipes for refrigerants, for heat transfer applications, liquefaction refrigerants, membrane materials, and also other applications, but also thermal storage materials, which is the second example I will share with you about thermal storage, how we calculated the material that stores heat, not electricity, it stores heat. And we call this our heat battery project, heat battery design. So here, again, we are using intelligent algorithms to compute the materials to be able to then design the heat battery with maximum efficiency. And that's another good example of how we use computers, how we also do the problem with a multi-scale systems approach. And importantly, also, it has to be sustainable. We need to not be shifting the burden, the environmental burden. You know, we can create a solution, store energy, but we can create a new problem. We don't want to do that. We want to solve the problem sustainably. And here we can think about how we can use abundant waste materials, such as plastics, and we can turn them into very interesting nanomaterials that can absorb heat in very efficient ways. And we can then go back to our engineering design and come up with a very good way to embed these materials in the roof, for example, of the house. And that's one of the applications that we are trying to commercialize at the moment. And this heat battery will be installed in a roof. It functions as a roof tile, but also it functions as a energy heat storage for you to use as a water heating in the home. And it also functions as a photovoltaic panel That means it also can collect solar energy for electrical applications. It's multifunctional, increases the efficiency, but also it uses sustainable materials built on computational optimization algorithms. It's a fantastic way to approach these problems rather than kind of solve them in a very siloed approach. Another example I think I will share very quickly and I will finish up. Here is how we can use waste in carbon mineralization. This is again chemistry, chemical engineering, and construction materials. And what we have here is this kind of approach to again install waste materials in construction materials, and importantly also our research incorporates carbon dioxide emissions. We want to always use carbon dioxide as a resource, and here any emissions that we may have in the process, we can bring them in together with waste materials, and we can create different blends of concretes, of products. But also what we can do is we can make them into pavements, and these pavements have already been installed and we are already rolling them out and commercializing this. What we are also trying to innovate is how we can do 3D printing of this concrete to make the product lightweight, strong, with certain other features and properties. So all of this is now being rolled out. This is an example of our first pavement that we've trialed on campus. Another one that we have trialed on campus recently as well. And also we are building more of these boutique elements, construction elements, 3D printed using advanced technology to do that, and very sustainable materials, low carbon materials. So this is an example of a roof tile, or a cosmetic tile with a abrasional element in it as well. That all means emissions reductions, industrial ecology systems working together to reduce emissions across the whole system, not just in one place. So I think that's important for me to stop here in the interest of time and allow anyone who has interest in this to comment. And I've got many other examples I can share, of course, and there will be hopefully other opportunities for us to meet with you. And of course, I would like to invite you to the School of Chemical Engineering at any time you wish. Please contact the team, contact me, and we can arrange for that visit for you to come in, preferably in your groups, it's better, but then we can discuss more about chemical engineering. So with that, I stop and open up for comments and questions and any discussions.
Thank you, Ali, for that great presentation. I'm sure all our students enjoyed. There's a question we have here from Ritu Singh. Does Australia manufacture its own solar panel or import them? What's the scope of getting a job in Australia if you do this degree?
In Australia, we currently import solar panels. A lot of the solar panels is manufactured overseas. Majority of it is manufactured in China. So we import a lot of it. Manufacturing is a problem in Australia, and of course, modern manufacturing is a big initiative by the government, and the government in Australia is addressing this problem. We know we need to reinvigorate manufacturing. So chemical engineering, sustainable manufacturing go together. And many of these processes that are such as renewable technologies, a lot of that, there is plenty of opportunity for us to begin this manufacturing. So in Australia, there is going to be manufacturing industries emerging for recycling these plants, solar panels. There will be emerging plants for recycling batteries and other renewable materials. So that's the first part of the question. The second question, Carlos? The second part?
The second question is, what's the scope of getting a job in Australia with a chemical engineering degree?
Very high scope. In fact, we have not updated data, but graduating with a chemical engineering degree gives you 100% employability. And the University of Sydney itself ranks very high on the employability scale. That means what's the percentage or likelihood of you finding a job after you graduate. It's we usually graduate students, and they always find opportunities and jobs. And I also would like to highlight this change in thinking about how I mentioned before, commercialization. We also support students quite a lot to create opportunities now. So rather than you going after the graduation to apply for jobs, we also support this pathway to create opportunity by spinning off companies, starting up business based on research innovations and so on. So this is a very active area now in University of Sydney in chemical engineering, and creating your own opportunities, you being a director of your own company, for example.
Ali, and your experience teaching here and with your students, where do most of them go to work? In terms of companies or in terms of roles, normally after they graduate? What are the most common roles they go to do, or companies they go to work?
There is quite a variety of different sectors that our students end up in. I should also mention, aside from the renewable sector, there is the food industry, which is a growing and big industry in Australia. There's a lot of people working in there, our graduates. Pharmaceuticals, nutraceuticals is another one. Chemicals, agrochemicals is another one. And also I should mention that our best students sometimes get snatched, and they go to work with consulting firms and banks and such businesses. So we often have our students graduating from our degree, and in fact they get jobs before they graduate. They get hired in the beginning of the 4th year, or just before they finish their final year. So it's quite amazing, I guess, that there is interest in chemical engineering always, because these companies and these industries, they know the value of the problem-solving skill set that our students graduate with. They're very versatile, very agile in companies, and they do often create a lot of returns for business and industry. So yeah, quite good opportunities for chemical engineering graduates. You're on mute, Carlos.
Oh, apologies. Thank you, Ali. We have 2 more questions here in the Q&A. Well, I think you already answered this one. Can you name some of the fields where the students end up, sectors after finishing this course?
Yes, I think I've answered that. I said in the energy, water is a very big area, water industry, that's a big problem. In the food, in the waste sector, that's an emerging sector. Lots of new developments happening there. We're going to need many more chemical engineers in the future, and pharmaceuticals in the health sector. In the digital world also, we work there. People work in the sustainability space and so on. So there is tremendous opportunities in all of the sectors, I would say, Carlos, for chemical engineers to contribute in.
And thank you, Ali. Here's a question from Ritu again. It says, are the jobs created in metro cities or remote areas?
There is emphasis on cities, of course, and urban development is very strong. We are a population in Australia that we live on the coast in big cities. Majority of the population is in large cities. Sydney itself is growing and becoming ever so much bigger. And there is, of course, big focus on such urban and cities. But at the same time, I mentioned earlier that there is quite an interesting move by government towards modern manufacturing. And also there is a move by the government to reinvigorate the regional areas. So there are a lot of the opportunities are beginning to emerge in regional areas. We in chemical engineering, we work a lot with regional areas, regional councils. They have big problems that chemical engineering, we are solving for them. Our students with our internship program, they end up also working in those councils, in those companies in regional areas. And they stay there for 6 months in the final year working in regional areas. So our internship program engages with companies outside of Sydney, not only in Sydney, but also overseas. So we do send students overseas to spend time in some cases in this internship that we have, which is a very important element in our chemical engineering degree at the University of Sydney.
Thank you for that great answer, Ali. And I think we have a question you just answered as well from Udit. He was asking about employment opportunities overseas. But I think that's what you're saying, right? The faculty, the school is very active, the academics are very active, our students are very sought after. That then if you happen to be an international student and you're going to go back to your country, those opportunities you created before you even leave.
That's correct. There's plenty of opportunities overseas as well in many sectors, industries as well.
And we have another question from Arcana. Is uni affiliated with some companies and assist students in getting job experience for future jobs?
Yes. Well, now our school in particular is very engaged with industry. We have extensive industry engagement programs. We not only work with them on research, so there's opportunity for the students to join the research projects, but also we have this internship program we call MIPS or ESIPS. And this program is for fourth-year students only, and it's for the performing students. And they spend 6 months in the industry with an industry project, solving an industry problem. It's like real work. It's really engaging with industry. And along the way, we also have many different industry engagement opportunities for the students. Every year we have that industry, they come in, or we send students to industry, and we engage with the industry on not only in research, but also in our teaching as well. Many of our academics also have companies, and they run industry projects through their companies, and are engaged in entrepreneurial projects, and that's an emerging area. So there is plenty of industry connection and engagement with the school.
Ali, one question. Many of our students, as you're aware, decide to study double degrees, and that's for many reasons they decide to study double degrees. In the case of chemical engineering, if a student was to decide, oh, look, a Bachelor of Engineering lasts for 4 years, double degree might be 5 or 5.5 years, what would you recommend them? Would you say, for example, those who want to do their own business, do a double degree with commerce, those that want to delve more into research, do with chemistry, or is there any recommendations with those students, or depends what they would like to do after they finish?
Well, yeah, I think this is a very important point. I think this is based on the interest of every individual student, and the opportunity is there. Some of them are aspiring students. They aspire to do engineering with commerce because they want to understand both worlds, and that's a very good thing. These degrees, double degrees, means that you do an extra year, 5 years, and you graduate with a double degree, and that's a very good thing because it allows those aspiring students, they want to work harder, they want to achieve, and they want to position themselves for the future, so in the career. But some of these degrees are, say, with science. They also are with other kind of technical based degrees. They combine, but it gives them an in-depth technical understanding that allows them to proceed further in research if they wish, because there's plenty of very interesting research opportunities and projects on campus across all the disciplines in chemical engineering and others. So, it's a choice, Carlos, I would say, that is very good for those aspiring students. It's not for everyone, but it is good in particular circumstances. It means longer time, and it means also that you will do more work. So you've got to be prepared for that.
Thank you for that, Ali. Yes, look, if some of you are thinking, oh, I'm still deciding between chemical engineering, chemistry, or science, or any other areas, you can do both as well, no? And this is what we tell with Ali. Chemical engineering has many benefits. You can see what you can do. Our students are very sought after, but double degrees also help. In any case, thank you very much for everyone who has been here today. Thank you very much to Professor Ali Abbas for this fantastic masterclass in his time today. We hope to see you next year in person. So Ali, any last words that you would like to tell the students?
I would like to thank them for their time, but also invite them at any time to reach out and to the school and to yourself, of course. And if they wish to visit the school, as I said earlier, they are very welcome to visit the school.
Thank you very much, Ali. Thank you very much, everyone who has been here today. Stay safe, and we'll see you next time on campus.